Hello and welcome back to my Physics Online Video Lecture Supplement series. In today's video I wanted to add a supplement video to the lecture that I delivered for the introductory physics classes. This one is a supplement for specifically the Physics with Calculus class, and it's a supplement to Lecture 9, which is on statics and equilibrium. And specifically what I am adding this to supplement is finding the center of mass for an object. To give a little bit of context to this video, I talked in my other lecture, which was lecture set 9 part 1, about finding the center of mass for a system of discrete objects. And to do that, you basically took the mass of each individual object in the system times the position of the object, you added them together, and then you divided by the total mass of the system. And you could do this in as many dimensions as you need to find the center mass of the entire system. So you might have an x, a y, and a z if you're using a truly three-dimensional system. The question, though, is what do you do if instead of having individual point masses, which is what these equations are mostly valid for, instead of having individual point masses, what do you do if you have a single extended object? And for that matter, what do you do if you have a system with more than one extended object? Well, the more than one extended object thing is not so much a problem. To find the center of mass for the system, these equations are still valid. You basically still find the mass times the position, except for that each individual object you can treat as being a point mass existing at the object's center of mass. So you basically have mass of object times center of mass for object 1 plus mass of object 2 times center of mass of object 2, etc. Where center of mass represents the position of the center of mass, and then you can divide that by the total mass of the system. So we still have to answer the other question, which is what happens if you want to try to find where the center of mass is for an extended object, an extended or continuous object. If you have an object which is extended and continuous, then there are a variety of ways in which you can approach finding the center of mass. If the object is a homogeneous object, that basically means it has uniform density throughout the object, it has maybe a symmetry to the object, then oftentimes the actual center of mass will be the center of the object itself. For example, if you have a marble, which is made out of, let's say, steel, and the steel has uniform density, the marble is perfectly shaped as a sphere, then the center of mass is going to be in the dead center of that marble. However, if you have something that is not symmetrical, or perhaps you have a variation of the density, then the center of mass may not be in the exact center of the object. For example, maybe instead of making a marble out of just steel, you make a marble that is partially out of steel and partially out of glass. And I don't mean a glass core and then a steel shell. That's still going to have a center of mass in the very center of the marble. I mean, maybe you do something weird, like maybe you have a glass marble and you hollow out one part of the marble and put like a bug in it or something cool to look at, so it has a sort of like a display inside the marble. Then you no longer have a marble that has uniform density, and the center of mass may no longer be the center of the marble. So how do you deal with this latter situation in which the center of mass cannot just be located in the center of the object? In other words, how do you deal with the non-symmetric situation? Well, what you do is you treat the object as if it is a system of many individual elements, each having some mass delta mi for individual mass. And we take the entire object to have a mass of m object. So add up all these little individual masses, you get the mass of the object. We take each of these individual elements and we say that it's located at some particular position r sub I. Then we say that we are concerned with such small individual elements that we have infinitesimal mass for each portion of this object. So that means that the center of mass can be given by this equation. So this is the limit as the little individual elemental masses are approaching zero of the sum of each individual mass times the position divided by the total mass of the object. This basically is the same equation that I used on the previous slide, but taking a limit as these masses approach zero. So this equation is the very same equation as taking the center of mass to be 1 over the total mass of the object times the integral of position within the object times the differential mass. This infinitesimal element dm is very often a function of the position. So let's see an example of what that might look like. This is a sledgehammer. In this example, we want to find the center of mass of a sledgehammer, given that the handle can be treated as a uniform cylinder and the head as a uniform box-shaped block, and that the handle basically meets the head in the center of this side. So the center of the handle touches the center of the face of the head. Center of the face of the handle, center of the face of the head. This handle, therefore, is not running all the way through the head. This is just to simplify the problem a little bit. What this basically means is that this length right here is 40.0 centimeters. I'm going to call this L sub h for length of handle. This right here is 4.00 centimeters because it is twice the radius. This side and this side are both given by 8.00 centimeters. And then the total length of this thing, it's basically this length right here, is 16.0 centimeters. The origin is being described as the middle of the handle opposite the hammer's head, so that's basically right here. So this right here is the origin point. So let's put a little arrow pointing out that this is the origin. And what we're going to do is basically two steps. First step is we're going to find the centers of mass for both the head and the handle. And so those are basically step 1A, step 1B. Then once we've done that, we'll mark those centers of mass as being, for example, here and somewhere inside the handle here, or inside the head here. Then the second step is that we find the center of mass for a system that's treated as having one object whose mass is the total mass of this head located at this center of mass, the other one being an object whose total mass is the mass of the handle located in this center of mass. And that gets us the final center of mass for the hammer. Alright, so our first step is going to be to find the center of mass for this handle. Now, what we've been given here for this handle is rho for wood, the density, which is mass per unit volume for the handle. And in order to find this one, we might start by drawing ourselves a diagram that looks something like this. So here is the handle. We have some particular section of the handle, and this section of the handle is going to have a mass of dm, which might be best represented as lambda times dx. And basically, lambda is defined as mass per unit length. That's to be contrasted with rho, which is mass per unit volume. So what we've been given is rho. What we really need to solve this problem is lambda. And the reason why this is lambda that we want and not rho is because if the cylinder has uniform density, then from an end-on view, the center of mass for the cylinder should in fact be the very center of the handle. Basically what this means is the center of mass for the rod is going to be R center mass rod is equal to whatever the x part is, I hat, plus 0j hat plus 0k hat. And the reason why we can put the 0i hat and 0k hat is because this right here is basically going to be lying along what we're defining to be the x-axis. Alright, so how do we get the lambda, mass per unit length? Well, one way of doing it is to find the total mass. So lambda is mass over length. So total mass is going to be whatever the mass per unit volume is times the volume divided by the length. And I note that the volume is actually going to be the cross-sectional area times the length. So this would basically be pi r squared times length. So lambda basically is going to look like rho times whatever the cross-sectional area is, pi r squared. All right, so r is 2 centimeters. Pi, of course, is the universal constant. If you multiply pi times r squared, you get 12.56. So now we multiply that by another 1.25, and we've got that the density is 15.7 grams per meter. All right, so now basically we would take an integral of basically x dx, because the x center of mass is basically going to be given by 1 over m times integral of x dm, which becomes 1 over m times integral from 0 to, I guess because of the way that this thing is oriented, we're going to negative L, if you will. And that is going to be x times lambda dx. And so what this all is going to give us is basically 1 over m times 1/2 x squared times lambda. So we'll just write this as a lambda over m from 0 to negative L. And that is going to, in fact, give us 1/2 of L squared times lambda is actually mass times L, so the masses cancel and we just end up with 1/2 of L. All right, so we've found the center of mass position for the handle. It's basically going to be negative 1/2 of L, which would be negative 20 centimeters I hat, because the length is 40 centimeters. All right, so to get the center of mass for the hammer, we basically want to take a cross-sectional area of the hammer's head, and we're going to actually integrate along this direction as well, the x direction. So draw this picture. Basically, an integral along the x direction would be to go along this square side that I've shaded here. And again, you can take a little sliver of the hammerhead, call it dm for the hammerhead, and once again you'll end up with a lambda times dx. So we repeat the process that we did before, and it'll end up being that the x center of mass is equal to 1 over the mass of the head times the integral of x times lambda dx once again. So it turns out that there wasn't anything special about the cylinder as compared to a block. You still get the same position. I'm going to actually call this x center of mass prime, however. And the reason why I'm going to do that is because, again, I want to integrate from 0 to negative L for the block, where this right here would be the length. So again, you're going to end up with x center of mass prime is equal to 1/2 times the length, which is going to be 4.00 centimeters. Now, the reason why I put this prime here is because that center of mass is 4 centimeters away from this edge. But this edge is itself 40 centimeters away from the origin. So the actual center of mass position for this head is going to be given by 4 centimeters plus 40 centimeters, and it was all in the negative direction, so 44.0 centimeters in the I hat direction. All right, so now our trick is that we've got to find where the center of mass of the entire system is. So step number 2, center of mass for the system. So our center of mass is basically going to be the sum of the individual masses times the positions of those individual masses divided by the total mass. So what that's going to look like is basically mass of the handle, which I'm going to call mass A, times position of the handle center of mass, plus mass of the head, which I'm going to call mass B, times R for B, the position of that center of mass, divided by mass A plus mass B. Now, what each of these masses is given by is this density times the total volume. So mass A is given by this density 1.25 grams per centimeter cubed times the volume, which was given by basically 40 centimeters times pi times 2 centimeters squared. This is length pi radius squared. So the mass of the handle is 502 grams. Actually 502.6 grams, so we'll call that 503 grams. And similarly, to get the mass of the head, we use the density of the head, which is 8.25 grams per cubic centimeter, and that's going to be times the length times the height times the width. So basically 4 centimeters squared times 16 centimeters. And so that means that the head has a mass of 2012. So mass of the head, 2,112 grams. All right, and the positions are these two positions that we actually found before, minus 20 I hat and minus 44 I hat. So this position again was minus 44 centimeters J hat. So the position of the center of mass is going to be given by minus 20 centimeters times the mass, which was 503 grams I hat, plus 2,112 grams times that position, which is minus 44.0 centimeters, also in the I hat direction, and that's going to be divided by 503 grams plus 2,112 grams. So when you put all these guys in and add them up, you end up finding that the center of mass position is negative 39.4 centimeters in the I hat direction. Or if you want, you could give a coordinate, which is to say that it's minus 39.4 centimeters, comma, 0, comma, 0. So now we found the center of mass of an extended object. And of course, I should give credit about where I found this extended object on the web. It's from a site called The Truth About Cars. And so hopefully you found this video helpful, and thanks for watching.